to you guys. So this is a loading screen. 1 second. So okay, this is like I said, IoT in easy mode. This is the outline. I'm not going to go through it. We have like 30 minutes, right? So let's just get right into the good details. Who am I? My name's Elvis. Like before, I got into IoT completely by accident. We'll go in that story for a little bit. Fun facts, I play games just like everyone else. I make music. That's really bad. I enjoy CTFs challenges. I'm always on CTFs. You can find me on Freenode doing stuff like that. I'm also on Twitter as Black Owl. So, okay, so IoT stuff, right? Everything that we have coming out is like, everything is getting the network stack, right? We have water bottles that can connect to your phone wirelessly and tell you when to drink water. It makes no sense, but, you know, we still have to look at these because they're still microcontrollers. So anyways, what kind of sparked all this research was that I had a former coworker that found a nice vulnerability inside of a Realtek chip. It was because he was running a fuzzer that he created for his TP-Link, just finding command injection, just straight up fuzzing, just whatever. Found it in 5 minutes, big deal. So I was like, whoa, well, let me look at my devices. Just like everyone else that's probably here, I have a bunch of electronic equipment in my, my closet, whatever. I just want to find what's going on. So like I said, this bug that he found was a big deal. So what I did was like, all right, I have this small Belkin device, and let me look for this unique string that it's responding with, which is BOA HTTP server, and it's got this. I was like, what is the actual attack surface for this, these type of devices? Because I don't know anyone else. I've never been to somebody's house where they're like, hey, check out my modem that's connected directly to the internet. No. But, just like everyone else that does research or anything like that, we go on Shodan, look for server BOA, and we have over 1 million results. Cool. So this is actually a legit, scale. We can actually maybe attack something and it could be a problem. So I was like, all right, I'll start digging into it. And so within just a few weeks, I found over about 12 vulnerabilities in different routers, different vendors. They all went from command injection, passing stuff that was from an HP instance over to system, or stack buffer overflows. Like, hey, I'm going to do a straight stir copy from this HP header. Great. So one thing that I failed at, though, when I was doing all this research was fuzzing. Just like my coworker did, Ricky Hedlazik. I fuzzed everything, up and down, left and right. I was doing Konami codes. Nothing was sticking. And it was getting me a little bit upset. I was trying to find command injection through every single HP, parameter, everything that was SOAP related, everything, nothing was working. So what I actually had to do was actually start looking at the firmware itself. And so the way I got started, you can get started as well. It's everyone's heard of Binwalk, most likely has ever done any IoT stuff or firmware related. It extracts stuff based on magic bytes or inside the binary itself. You can parse out the squash.fs, get your binaries, throw in the IDA or radar, whatever you use for disassembly, and start going at it. So, but at the same time, we have all these microprocessors, and if a lot of us are in the x86-64 space, we may not know, thank you, the assembly instructions that go on for this, and nobody wants to read a big manual for MIPS 32 assembly. It's just boring and kind of tedious, right? So what we can do instead is that we can build a toolkit, you can say, and have these cross compilers, and we can make C code that we know what to do. We make C, so let's just have the compiler spit out the instructions. So right off the bat, I'm like, all right, I'm going to initialize a integer variable of 0. So we have a 0 register being populated into that stack address, frame pointer address. Awesome. Going forward, hey, 68 in decimals, hex 44, argument value 1 being passed to my function. So we also see A0. Okay, when I see A0 being populated, it's going to be an argument to some sort of function. Same thing with the second one, A1 with the second argument. And then we have the return. So we have hex 66, and just like before, it's the same frame pointer offset for my ret value. So now we know that V0 is going to be a return value from a function. And then we can just keep going, like printf. This is the second argument. Again, we see A1. So we can use these type of things, and then the 4343. And then also to dig into this, I saw this ORI instructions, and I was like, well, what did they kind of do? It's kind of ambiguous, right? And looking at the assembly, manual and stuff like that, it may seem a little bit ambiguous. But what we can do when we're not sure about assembly instructions is that we can set breakpoints, right? We can set breakpoints and see it visually. So set a breakpoint at these two instructions. I look at the very first value, and I set step mode on into GDB, I step mode 1, and I look at the, make sure I'm, executing the instruction, then look at the output, and I see that 43 is in the most significant side. Cool. So now I have an idea, a visual concept of what LUI does. do another step 1, and then look at it again, and I see that, all right, lower bytes, cool. So now I can start getting like kind of like an idea. So whenever I'm looking at radar or IDA, I can do manual analysis a lot quicker instead of just looking at the manual and trying to figure things out. We can do this quicker and faster. So okay, so we have all these binaries, we have all this firmware out there. We can probably extract it. We can do all these fun things. But what's better than just looking at assembly? Like, well, not really better, but what we can do is learn about GPL, right? A lot of these devices are on the GNU public license. And a lot of these things, right, provide source code for these binaries. So we can kind of take the easy route, kind of go on Google and go, well, how about firmware for this vendor? Cool. I can download the source code for that firmware and have all the binaries and all the source code for that. So instead of looking at IDA, which is a great way, we can also look at the source code to get a better idea of what each function does or what we can do to manipulate memory in our favor. Going forward, I have a TV. It's on a GPL. Great. I also have other firmware for another vendor. I'm blurring out vendor names because this is not supposed to be vendor like shaming or anything like that at all. This is just the idea that this is out there, this is how you can get started, and I'll show you some more. The list goes on and on and on. So okay, so I'm talking about software. I talked about how if you have C, you can kind of get started off the bat and start teaching yourself the assembly for your target architecture. It would be MIPS, ARM, or whatever. So your IoT shopping list. So if you just want to get started, you can get started for very, very little. It says $100, but that's everything brand new, brand spanking new. If you like everything brand new, $100 will get you all the available tools that you need to do in order to get hacking, right? So the first things is the serial interface. It's a FTDI, FT232H breakout board by Adafruit. It's great. It does SPI, JTAG, I2C, and UART. It's fantastic, and it's $15. So if you blow it up, who cares, right? From there, you going forward, like you get a multimeter to check for ground, you're checking for DC power, all that good stuff, and then your soldering iron to solder header pins, and then your miscellaneous stuff to, get soldering, right? As you go on and you start, becoming more advanced, you're going to start, integrating and buying more things, and the list goes on and on and on, and you can build yourself the super lab of your dreams for like over $2,000, and it just goes on. But you don't need that. You can start with the bare bones stuff, get creative with what you have, and go forward if you need to. But for a lot of IoT devices or router stuff, you only need the beginner stuff. You don't need to invest a lot of money into this. In fact, you can buy a lot of these used, except for the FT232H. But you can buy like a used soldering iron. If you have a buddy that has a multimeter, it's just got laying around, you can borrow that. You can do it for a lot cheaper. You don't need to spend money for this. So to talk about the hardware stuff, I want to talk about like UART. So as a lot of people may know, UART is a serial interface. It looks like you just telnet it into a device or SSH and you got that command line, right? If it's a Linux operating system. So finding UART, you can do it without opening up the box. You don't have to open up the box. If you're worried about, I'm going to void the warranty, that's cool. You don't need it. So every single wireless device out there has to go through FCC qualifications, right? And it has something called an FCC ID. You can go on the FCC's website, like this, and you can find the internal photos. Awesome! They've taken this thing apart for me, so I don't have to take it apart and possibly cause some damage because I'm a little on the, being careful, right? So I open up the internal photos and boom. I start seeing kind of like a pattern. A lot of people in here who have ever done this kind of stuff before recognize that pattern. Those 5 pins right there that are not soldered. It looks like UART. It looks like a serial interface. So let's try it out. So, first things first. So one thing I've done by accident, and I don't want anyone else to do what I did, find ground first. I have plugged power into ground before, and it's not fun. So you always want to find ground. And the way I did it, that is the ground pin, because with this multimeter, it is sound feedback, right? Once I find ground, it'll go, and you'll get your ground. If it doesn't have sound emissions, it's kind of a pain to have to look at the multimeter and see if it's continuity or not. So this is a common ground that I found out as well. Not everything uses ground like this, but it's a good start, right? So once you find ground, remember, connect ground to ground. Never click, put +5 or +3 or whatever into ground. It's something I'm still kicking myself about. But this is like a high level stuff. This is just how it works. Transmit to receive, receive to transmit. Just like a phone call. You put up your ear to the receive, and your ear receives, and somebody talks. It's the same thing, just with computers, right? But if you don't want to brute force around for the TX for the transmit on the device and you want to use a logic analyzer, you can do that too. And I can show you how to calculate the baud rate and all that stuff so you're not brute forcing. So you're not like, I found the TX pin, but I'm getting garbage and I have to let me try it again, attach screen to this device using like 9600, 11500, whatever. It gets kind of annoying to brute force these things. But if you have a logic analyzer, we can take like a 20-second digital capture, which is great, but we're going to pretend we're CSI Cyber, and we enhance, and we get this. So what I'm looking for in this entire thing is the shortest width bit, right? This is the shortest amount when the falling edge and the rising edge happens again. It goes down and goes up, and in this case, it's 8.8 microseconds. So with that, we can calculate. And so if we take 1 second over the shortest bit length divided by the amount of seconds, like microseconds, whatever it is, we can get the baud rate. And if anyone's ever used a Soleil logic analyzer, they do have like protocol decoders, and there's a serial one. So I put my 113636 whatever, which is about 115200, right, for standards. But if I plug in this number right into here and have it analyze the protocol, it will tell me this is the word start with the space. Great. So now I know the baud rate, I know the port, everything else to get started, and this is just basic UART. And it's very, very easy. You may come into the future where you have password protected UART, just like you have with Telnet and stuff like that, but there's ways around it as well. I will talk about that maybe offline if you guys are interested, about booting to single user mode to bypass these type of things. Or later on in the talk, I'll also talk about pulling off flash chips that talk over the SPI protocol in order to dump everything that's inside of it. So speaking of that, so this is my little like a little repeater thing that I have laying around. The image is a little bad. I apologize for that. But just again, enhance, and I found the serial number for this. This is the MX25L1606E. And when you just use Google, because everything is great when you use Google, you'll find the data sheet. The data sheet will tell you everything about this chip. It will tell you how it works. It will tell you the commands that it has, and it will tell you what the pins do. Just like this. It's an 8-pin. It tells me where the power and ground is, VCC power. It will tell me where the clock is. It will tell me where the input, output, and also further down the document, it will tell me which pins I have to short in order to get into a particular mode so I can start readings from it. And it will also tell me the commands I can use to send to it over the SPI protocol to be like, read this amount of data and send it back. And it's very, very simple. We can also use our logic analyzer, so when we just hook it straight up and we just probe to it, when the device is talking to it, we can verify that when there's a rising edge or anything else like that, it matches exactly this. So we can say, this is exactly the right data sheet, I know how to talk to it, we can pull it off, or we can use something called an SOIC, in this case 8 for 8 pins, probe thing, for SOIC 8 clip, sorry, and we can just attach the leads off of it and do everything ourselves. We have to be careful with this, because if we're doing power, we're supplying power to when the thing is off, we may break other components. It's a maybe, but not always. So I always like to remove the flash chip, but if you don't want to be intuitive, you don't want to possibly break something, you can always clip onto it. This clip is about $6, and it's awesome. So, okay, so what about exploitation, right? Like, who cares? Yeah, I have a device, I can talk to it, but I want to exploit this. I want to, like, if I have a buffer overflow, I want to exploit this. I'm with you. So, a lot of software out there that, maybe some binaries, whatever. A lot of people are very verbose about error messages, very verbose over the serial interface. So, for example, this may or may not be a 0-day against something, who knows? But you can see the return address is now 43434343, which is all capital C's. So this is an indicator of a stack buffer overflow because the return address is being corrupted. So just to verify it, I can do that as well. And if anyone's ever done any kind of stack buffer overflow exploitations, what do? Pattern create, pattern offset, boom, run away, right? Great. So you can analyze the crash. You can also use something called QEMU to emulate the binary, whether it be a full-blown VM or just userland QEMU using statically built userland QEMU in a CH root environment. But you can create your own exploit, but you have to be careful about the libraries because they do shift around, so you have to jump by offset, but we'll talk about that later. And create your exploit. If you have JTAG, you win. You hands down win, because you have complete control over the processor itself. And I will talk more about this. So JTAG, you can actually have a GDB instance to the processor itself and set breakpoints and analyze everything. So you already win. You can craft your exploit right there on the box using JTAG, and it's very, very handy. If you don't have JTAG, you're going to have to start emulating some stuff. Or you can start recreating what the code looks like in assembly, make it in C, and start making your templates for your ROP chain or whatever you need to do, like if NX is enabled. But you can also look at the processor, because some processors don't support NX. So the first thing I always like to do is always cat the processor, the process I'm looking at, get the maps. so I can know my libc addresses and all that good stuff, so I can route via offset. So everything else is on here, but the slides will be available, and that's all the good stuff. But I wanted to show that when you emulate in QEMU, using QEMU, you can also take your same exact payload, which is, this is from my DVRF project, Damn Vulnerable Router Firmware. And so this is the stack buffer overflow one. I have a function in here that will call system slash, bin slash station system and also exit. Take that same exploit and I change the, the padding a little bit, but it's the same offset, same everything, and I still get the same output. Was able to hit that function that is not called anywhere else. So the stack buffer overflow did work on both the QEMU environment and the actual device. So this is an Arduino Zero. It uses a Cortex processor by ARM. So there's no memory management on it at all. This is when you start running into devices that use real-time stuff. They start using binaries that don't really need a full-fledged operating system and does trivial tasks, like every so cycles I'm going to check out this sensor or whatever. So I'm also creating some vulnerable applications for this thing as well, so it forces you to use JTAG. So you have to start using JTAG in order to create your exploits. And if you do this, you will be able to do it on actual devices and going forward. This is the JTAGulator as well. It's a bit expensive. And I'm currently working to see if I can make a much cheaper one so people can get into this kind of space without spending a lot of money. So this is just a quick output from JTAGulator. You find your input, your output, your clock, and it's great. You can also test it to make sure that it's the right ports, because sometimes with the JTAGulator, you do get false positives. So with that, when you use JTAG, people will throw JTAG everywhere, but not a lot of people know how to use it. So one thing that I use is something called OpenOCD, which is on-chip debugger. And from here, you can create a configuration. We can talk about this offline, about creating a configuration file so to talk to the processor directly in order to get a GDB instance. So when you start connecting to it, you'll start seeing that GDB did open. I have this certain processor and I have 6 hardware breakpoints. Awesome. So when it launches, the default one for OpenOCD will open a listening port on port 3333 locally. So you connect to it 127, just localhost 3333 with GDB for that target architecture. Just target remote that, and you'll start getting everything. And you can start dumping memory. Look at the datasheet for that Cortex processor and see what memory areas are for what purpose. So not everything. You're not going to get a device that's going to use, null to all Fs for 32-bit space. You're not going to have 4 gigs. So you're going to find the specific areas and you can dump all that stuff and you might get some useful information. Like for example, on one thing I saw the AES keys right there in plain text and ASCII in memory, and I was able to pull that down for some sort of protocol. I can't go into that right now. But there's also a Tellin Interface, so you can talk to OpenOCD directly and say, I want to maybe halt the processor, I want to restart all this, I want to restart but don't do anything, halt the processor, and you can start doing help, and it'll give you a bunch of things. This is just to get started. You can measure the clock, you can start your JTAG interface and start launching the GDB instance. So okay, so we're kind of wrapping up towards the end of this. So I have something I'm working on, and it's for everybody. I got the idea randomly one day, when I was inspired by something called a damn vulnerable web app, damn vulnerable Linux, whatever, right? There's so many of these. But I didn't find anything that was a hands-on experience for routers, for any kind of embedded devices. And since we're, we're living in a world where everything's getting a network stack, which is a bit silly in my opinion, but I'm not going to go into it. This is one way that I'm starting to bring back to the community to say, this is how you can get started for very, very cheap. You don't need to have this particular device. I did have an old Linksys E1550 laying around, which is a MIP32 little Indian architecture, and I made vulnerable applications for it. It's a real binary that you can upload to your router, and it will accept it, it will install it, it works great, but you can also emulate it, and I encourage people to do emulations as well. You can do both ways. So, and also, anyone who's developing for IoT and is interested about exploitation or memory corruption for their architecture and stuff like that can play with this. So for now, like I said, it's only MIPS32, but I am going to go forward and start developing for other architectures, and if other people want to join in on that, it's great as well. It's supposed to be for the entire community. So this is where you can download it. GitHub, awesome. You can fork it, you can download it, do whatever you want, and I will be posting the source code in about a few days so you can build it yourself instead of having just the raw binary. So, future plans, I'm going to, like I said, continue development on DVRF. I'm going to, expand it on a bit. I'm going to be looking at RTOS-based stuff, so for that Arduino Zero, so you can start exploiting things that don't have a full-fledged operating system or a command line interface that you have in serial. I'll be creating blog posts on my company's blog, which is Praetorian. It would be anything from basic exploitation. So like, hey, how do I do this stack buffer overflow like in x86, jump ESP or whatever, right? That's pretty basic. Or anything that does use NX and how to like ROP into that, and maybe like, all right, so like I have libc and stuff like that. How do I actually create this ROP chain for this architecture? Well, I can start showing you. If you know ROPing in x86, you're putting pointers on the stack. Well, I can show you exactly the equivalent of that, and I'm going to be writing about that as well. But for every single level that I solve for my DBRF that I put on the internet, there will be a new challenge out there. So this is, again, it's supposed to be an ongoing thing, people to learn about exploitation, hardware stuff, the complete hardware and software stack. And I'll also go on to like future stuff, because I believe the FCC just came out a few days ago saying they want to start hardening firmware. They want to start locking down these things and make it more secure, yada, yada, yada. And also there's hardware protections. Like the silliest ones I've seen is where the JTAG traceouts, when you look at the pins, are just cut. So you can just put like maybe some continuity there, boom, you got JTAG. Or they just completely disable it altogether, but that's another story. And once I dig into that a little bit further, I'll be posting about that so you guys can be more aware and also be having more fun with your hardware. So, and again, anything that I find that is electronic, if I go to like Fry's or any kind of like electronic store, I'm buying it, I'm destroying it, I'm looking around. That water bottle, I'm still on that waiting list from Kickstarter. So, it's going to be some fun stuff, and I want you guys to also get involved into hardware hacking, especially if you're interested. Don't be intimidated by hardware. The easiest thing you can do is go to Goodwill, and they have routers out there for $5, $2, and they're like current routers, like current Linksys, Netgear, whatever, Asus. And you can just buy these things and take them apart. They're $2. If you break it, who cares, right? Start playing around with these things, and then take it to your more expensive products that you want to take apart as well. There's a $400 watch or whatever it is. You can do these things, and it's very, very easy. But I'm going to provide the hands-on experience so you guys can learn from it, instead of just writing about blogs that people can read but not actually do. So, again, I'm going to put this online and everything else. So these are like the hardware stuff for the beginner stuff, where to buy them, all that good stuff. There's blogs out there to get started. I'm always available on Twitter as well. So if you have any questions, concerns, I'm always there to help out. I will not hold your hand for exploitation or anything like that. I will point you in the right direction and make you learn. So that's my promise to you guys. And this is the end of my talk. So any questions? Yes, the guy in the back. What? Huh? I am planning that for possibly by the end of March. So I'm making sure I got my sockets and everything all ready, and they're working great, and I make sure I can create exploit for it. So I don't want to send something out that's like, hey, yeah, it's vulnerable, but I can't exploit it. That makes no sense. Yes?
What JTAG debugger do you normally use? Do you use the 232? What do you actually use for your JTAG debugger?
So for my JTAG interface, I did use the FT232H. If you heard of the Shikro as well that does that, it's the same FTDI chip, but I use that as the interface. Any more questions, concerns, comments? Okay. Cool. Thank you.
Okay, great. Thank you. Just like to thank you for sharing your valuable knowledge, Elvis. And on behalf of BSides and Fitbit, I'd like to give you a Fitbit.
Oh, great.
Thank you.
So there may be an exploit for this pretty soon. Stay tuned.
And please do not leave yet. We have an announcement to make.
Just a quick announcement. So, in about an hour, we actually have food downstairs. There's going to be an open bar, but you need to get drink tickets first. And then we're doing a raffle for a pair of high-end Beats headphones. So, if you haven't gotten a card to fill out, I think there's probably maybe 125 of them left. You might want to go do that after this. So, thanks for coming.